Aaron, you can send your presentation to via chat to us, and we will upload it.
I think I can screen it myself.
Yeah, it will be nice.
I can do it myself. I will share the screen with you.
Yeah, good, excellent. So we will wait a bit. Yeah, so I will try to announce your lecture right now, and you will please do. So, so this is my great pleasure to give a floor to my good friend Aaron Chechanover. He's a Nobel Prize winner, you know, and we met each other in China many years ago, and together we worked in one council committee in the biomedical engineering college, and we spent many happy time in China. And I met also Aaron in Sochi, where he presented his plenary talk a couple of years ago. Unfortunately, this year this meeting was canceled, and but we have a good opportunity to meet here in Saratov. So we will wait a bit, and Aaron will solve his problem. And oh, excellent, good.
Okay, can you hear me?
Yeah, excellent, thank you.
Okay, so my name is Aaron Chechanover. I'm on the Faculty of Medicine at the Technion, which is Israel Institute of Technology in Haifa, Israel. And currently in my laboratory, you see the beautiful city of Haifa. It's truly a gorgeous city. You see the Baha'i Gardens. I'm sorry I cannot be with you today due to the pandemic, though I would love to come to Saratov. Next time, I've been to Russia many times. And hopefully once the pandemic will settle down, I'll be able to visit you physically. I'm a physician, a surgeon, and a biologist by training, so I'm not sure what I'm doing exactly in an optics and biophotonics meeting, but as an opening lecture, I'll give you a little view of what's going on in some other sciences that optics and biophotonics are closely related to the physical side. And I will present to you the biological and medical side. And I'm going to talk about the revolution of personalized medicine and the dream of people to cure all diseases. Is the dream realistic? Are we approaching it? Is it possible at all? So I cannot, okay. So you see that, you know, the dream is of people to remain young forever. Everybody wants to remain young, and everybody wants to live forever. So we want not only to remain young, but to be completely free from diseases. And there are many books that have written on this. I just show you one of them, A Cure for All Diseases, and so on and so forth. And I think that the best thing to do is to look into history and to ask ourselves whether it's possible. Well, it depends on the eyes of the beholder. If we are thinking of human beings about 120 years ago, at the turn of the 19th century to become the 20th century, then the average lifetime was at that time around 50, 55 years. So merely 120 years ago, people were living only 50 or 55 years, which in our eyes is extremely short, when in the developed countries, people are living now more than 80 years. The average lifespan in the developed countries is now something between 82 to 83 to men, about 85 to women, which is more than 35 years above the average merely 120 years ago. Then, if we go 4,000 years ago to the old Greek time and Roman time and Egyptian time and Babylonian, and of course the Chinese that were far away from us and did not connect, the cultures did not connect, the average lifetime at that time was about 30, 35 years. So it took almost 4,000 years for people to extend their life from 35 to 50. And then in one century, one single century, the 20th century, we extended life by 35 years. We added almost 60% to our lifespan. So looking at the number, people say, hey, why not? Maybe in the 21st century, we shall add another 60%, and we shall add 50 years to our lifespan. And by the end of the century, we are going to live 140, 150 years. Well, this probably is not going to happen because of mutations, because of exhaustion of biological systems. There is an end to every machine that we know. But the prediction is that we are still going to make it to about 110, 115 years on the average. And the question will be, of course, in what quality of life? Are we going to enjoy 110, 115 years being healthy? Or, you know, we are going to suffer from vascular diseases, from brain diseases, and we are going to be a burden on the society, an economic burden that the society will not be able to sustain. So these are still open questions. As physicians and as scientists, we don't ask these questions. We are spending time in the laboratory with an effort to cure diseases. We are, in my laboratory, we are working on cancer. Several drugs against cancers, very successful drugs, have been developed based on our discovery, and more are in the pipeline. So we are not thinking about the epidemiology of aging. We are thinking of the pathology of diseases, and that's exactly what I want to talk to you today. I believe that cancer is going to be the first victim. We know a lot about cancer nowadays, and I think that we are on the way, I hope, to defeat cancer. We know much less on brain diseases, on Alzheimer and Parkinson, but this will also come. And the question is, what will happen if we are going to defeat these diseases? What's else left? Cardiac diseases, yes, we are doing quite well on heart diseases, not curing them yet, but understanding very well what's going on them. They are very good drugs for reducing the level of cholesterol and so on and so forth. But we don't know what will happen in the future. We don't know what new diseases will come. Think about cancer. You know, 120 years ago, people did not die of cancer. They died of infectious diseases, of bacteria. They died of pandemics, of the big flu pandemic. Now we are facing another pandemic, and already the number of the people that died of corona is exceeding the number of people that died of in the big pandemic of flu 100 years ago. So in several countries. So white people did not die of cancer 120 years ago because they did not live long enough to get cancer. People did not die of heart attacks 120 years ago because they didn't live long enough to get heart attack. People didn't die of Alzheimer because Alzheimer is a bona fide disease of a more advanced age. Women died during delivery. People died of diphtheria, of tetanus, of polio, of other infections. They died in wars. So we see that the main killers of today, if we think about it, like cancer, like brain diseases, like heart diseases, are all diseases of age. Basically, this is the price that we are paying in order to live longer. Because at the age of 50, typically we don't suffer of any of these diseases. So as we extended life by virtue of antibiotics, by virtue of vaccinations, by virtue of diet, by virtue of developed medicine, X-ray, CT scan, MRI, and so on and so forth, all the achievements of medicine, we extended life, but with it, we are also paying a price. And the price are new diseases that came up that are diseases of more advanced age, like cancer, brain diseases, and heart diseases. So once we are going to defeat cancer and to defeat brain diseases and to defeat heart diseases and live longer, let's say 110, 115, 120, we don't know what is waiting for us behind the corner. Maybe some new diseases will come up. So the mystery is still around the corner. But we are not prophets and we are not futurists. We want to deal with current contemporary problems. So let's go to current medicine. And medicine is moving in several directions these days. Medicine is going in a replacement of organs, initially with artificial organs. We are now can replace joints with metals, with titanium joints. We are able to replace heart valves. So we are able to replace deteriorated organs, some of them, with new artificial one. But there is apparently a limit to that. We cannot replace artificial kidneys. We cannot replace still artificial heart. It's amazing that the heart is a simple pump, and nevertheless, we cannot generate an artificial pump that will replace the heart only for very short periods of time, but not for a long time. And we are completely dependent on transplantation of organs from either donors or dead people. So we are able to transfer organs from one patient to another. Again, we still have to fight rejection by the immune system, and the patients that are getting transplants are dependent for the rest of their lives on immune suppression therapy. So one direction that medicine is going is, of course, artificial organs and what we call engineering, true engineering. Another direction, which is very similar to this one, is what we call stem cell biology. We are trying to replace organs by new organs that have been generated from stem cells, from reprogrammed stem cells. So we are able to take cells. There is already one Nobel Prize awarded for this discovery to a Japanese scientist, Shinya Yamanaka, and another British scientist, Sir John Gurdon. And the idea is to take cells and to reprogram their DNA so they will become new organs. This idea is still at a very primitive, very embryonic stage. We are still far away from being there. We are not talking even about whole organs like kidney, like eye, like lung. We are talking about islands of cells that may replace islands of cells that have been degenerated, like in diabetes. In diabetes, for example, which is an epidemic. Diabetes is a huge epidemic. What is missing is a hormone called insulin, which is in charge of the glucose metabolism and of the sugar metabolism to bring sugar into cells. So we are able to use it as a source of energy. And the insulin is a hormone that is responsible for transport of the sugar from the blood, from the outside of the cells into the cells. So the cells will be able to use it as a fuel. And insulin is not secreted anymore by islands, by cells that are residing in the pancreas. They are called Langerhans islets. And therefore, people have tried for many years to reprogram embryonic cells to generate new cells that will secrete insulin, so far with no success. So the whole idea of stem cell, it's still at its very, very beginning. There is a big hope that it will be successful in the future, but still we are not there yet. And the third direction, beside artificial organ and stem cell reprogrammed organ, is drug discovery. You know, drugs, we are using a lot of drugs. We are going to the pharmacy with a prescription for the physician, and we are buying drugs. And the question is how the drugs are coming to the pharmacy. It's taken a long way to bring a drug to the pharmacy, typically 5 to 10 years. The development of vaccines to COVID-19 was a miracle. It took several months to develop this new drug, but it is all based on already known knowledge from molecular biology. What is DNA, what is RNA, what are proteins, a lot of knowledge in immunology, a lot of knowledge in nanotechnology, in packaging, the messenger RNA, and so on and so forth, but this was amazingly fast. So we shall concentrate I shall concentrate my talk only on drug discovery, and I will go very quickly on that. So the first revolution of drug discovery was an era of incidental discoveries. People didn't mean to discover a drug, but nevertheless they discovered. I will bring one example, and that's penicillin, the first antibiotic. It was discovered by complete coincidence by Sir Alexander Fleming. You see him on the flag, on the stamps on the left upper side of the slide. And you can see here in the middle, you can see the dish, and you see the smear of bacteria. For those of you, the physicists who are not trained in biology, these are bacteria. And Fleming did a mistake, and he forgot the dish, which contains a very rich, nutritious media, open on the desk, and a spore of a fungus fell on the dish and grew to make this white colony. And you see that, sorry for that, that between the bacteria and the fungus, there is a halo that the bacteria cannot grow. And Fleming suggested and thought that the fungus, the penicillin fungus, secretes a material that he called antibiotics, anti against, bios, life, that prevents the growth of the bacteria all the way to the border of the colony. And the material, his suggestion was correct, his prophecy was correct. Penicillin was isolated by Florey and Chain. All the three of them got the Nobel Prize for medicine, and penicillin was introduced into the market already in 44 and 45 and being used by the Allies during their invasion to Europe, to Normandy. And then many more antibiotics were developed based on the same principle that fungi secrete antibiotics. Streptomycin was developed, and this was one of the most important discoveries ever in medicine that really rescued the lives of hundreds of millions of people along the years. And it was coincidence. You see, this was just a coincidence that the fungus grew on the dish, on the nutritious dish that bacteria were supposed to grow in. But serendipity is not the way to develop drugs, and people move to a more systematic way, and that's called high throughput, the brute force screening, and that reflects the development of modeling of diseases. We can now model many diseases by growing cells, just isolated cells, from cancer, from Alzheimer, from heart diseases, and then we can try numerous chemicals that have been accumulated during synthetic processes. There are libraries of hundreds of thousands of chemicals, and we can try them one by one by one by one, and until one of them will somehow, by chance, will prevent, will inhibit the pathologic process, like accumulation of cholesterol. And I bring you just one drug that was developed based on screening. The drug is statin. Statin is a very successful drug to prevent accumulation of cholesterol in the heart, in the arteries, in the vasculature of the heart. You see here the cholesterol that grows and occludes the vascular system in the heart. And once the occlusion is complete, people are suffering from heart attack and typically die. And Akira Endo, a Japanese scientist working in a pharmaceutical company, screened a library of chemicals from plants, from trees and from fungi in Japan when he was working in a pharmaceutical company in Japan. And he found one drug, one material, one compound that prevents the cholesterol synthesis, prevents generation of cholesterol. The drug was further developed to become an extremely successful drug, and statins are being sold these days for tens of billions of dollars every year, tens of billions of dollars every year, and it had become one of the most successful drugs in the pharmaceutical market. So the question is, why not to screen? Now screening is systematic. We can screen and screen and screen and screen for models of all diseases. The issue is the model. The model are typically cells or mice, and mice are not people. And therefore, we needed to move to another approach, and we are just started to move into it. And it's called the approach of personalized medicine, personalized or precise, which is also predictive, preventive, and participatory. And I will talk about it all. And the reason that we moved into it from screening is the following, that if you take a group of patients on the left side, and let's say that they have disease, they have prostate cancer, breast cancer, Alzheimer's, doesn't matter. And we just look at them as colored with three colors, green, blue, and orange, and we start to follow them, we start to treat them. We see that after a few years, some of them die. Unfortunately, the ones that are marked with X, the blue and orange are dying, while the other ones are alive. Some of them are cured, some of them become chronic patients, and so on. And the question was, what is it that the same people, that the people with the same disease behave so differently? Why is it that people are not behaving the same, are not responding the same to the same treatment? And the reason is the following. We are not the same. We are not identical. There are not two people that walk on the face of earth that are identical to one another. We are tall and low. We are fat and thin. We are male and females. We are exposed to different climates. We are exposed to different diets. And mostly, we inherited from our parents a different genetic repertoire. As I said, there are no two people. There are no two people that walk on the face of earth, not even identical twins, that are identical, that are truly identical to one another. And therefore, no wonder that despite the fact that we might get the so-called similar disease, like breast cancer, Alzheimer's, heart attack, doesn't matter which, we are responding differently to the drugs. And that notion, that knowledge, that realization required a special approach. And the approach came by the Genome Project, where we able only 20 years ago to sequence the entire genome of one person. And it took a lot of time and a lot of money. It took more than 7 years and almost $1 billion to sequence one genome. But in the last 20 years, the technology has become very common, and we are now able to sequence the genome in a few hours with an expense of $2,000 to $3,000, and the price and the speed are still going down very quickly, and it becomes a routine examination. We are able to sequence, we shall able to sequence within 1 or 2 or 3 years the genome of each and every one of us for less than $1,000 and within less than an hour. And the sequencer, the machine, will be on the table of every physician. The information will be available very quickly. And by doing so, we shall be able to diagnose diseases, the mutations that are behind the diseases very quickly and very efficiently, and to design a drug not to the disease, but to the mutation. And the drugs of the future are going to be based completely on our DNA. You see here Adam and Eve in an illustration on the Time magazine. And on the right side, you see the drugs of the future. Amazing new medicines will be based on DNA. And we are going to move from a one-size-fits-all medicine that we are treating tumors with the same tools for all patients, from chemotherapy to surgery, to a tailor-made medicine that we are going to tailor the treatment to the disease, to the characteristics of the disease, to the DNA repertoire, to the mutations of each patient. And I want to bring you just one example, breast cancer. And I look at these two biopsies on the left lower side. These are biopsies, samples taken from breast cancer of two different women, woman A on the left side, woman B on the right side. And you can see that the biopsies are very different from one another. You see that the tumor on the left side is one piece, while the tumor on the right side, it's the same magnification, is scattered into islands. But what is most important is the manipulation that we did on the tumor. On the right side, the tumor is being stained. It is being stained with an antibody to a mutated estrogen receptor. Estrogen receptor is one of the hormonal receptors, the typical to women, and the staining with an antibody is specific to a mutation in the estrogen receptor of this woman that drives, that is the catalyst of the cancer in this woman. The woman on the left side, the treatment of the sample was the same staining, but the antibody didn't catch. You cannot stain it. So the woman on the right side has a mutation in the estrogen receptor, while the woman on the left side has a mutation in something else. Maybe the progesterone receptor, maybe the EGF receptor, but something completely else. Therefore, the woman on the right side can be treated with tamoxifen, which is a drug that is specific to mutation in the estrogen receptor, while treatment of the woman on the left side with tamoxifen will be useless. It will be waste of money and waste of time. The disease will still continue. So you see that now we are looking for the molecular mechanism that is behind the disease. And if you want to have a metaphor, since I like to drive cars, I'll bring you a metaphor from driving. If you are getting up in cold Moscow in the winter or Saratov, and the car doesn't turn on, the disease name is the drug, the car does not turn on. But the reason for the car not to be turned on can be multiple. It can be that because of the rain, the sparks are wet. It can be that you forgot the lights and the battery is empty. It can be that you forgot to put gas and there is no gas, there is no oil. It can be that you didn't lubricate the car and there is no oil in the cylinders and the cylinders get stuck in the barrel. It can be that the battery is too cold and cannot send the spark. So the reason to the disease can be different, though the disease appears the same. So the car does not turn on, but two cars that do not turn on, the reason for that can be different. And if you treat the car with the wrong reason, the car will still not turn on. Now, this realization came to medicine as well and led to a big revolution in which we are looking for the reason of the disease by sequencing the DNA of each and every patient. We are still not there. We are at the beginning. We are starting to do it for several cancers and several diseases. But once we have a full map of all the reasons that lead to breast cancer, we shall be able also to design appropriate drug using very sophisticated chemistry to treat all diseases. And people today think that there are about 20 different reasons for breast cancer. So breast cancer doesn't stem from one mutation, not for two, not from three, but rather from 20, and each of them will need a specific treatment. So woman A might have a problem with the EGF receptor and she might need Herceptin and so on and so forth. And with sophisticated chemistry, we are able now to map the mutations and then to design drugs that will fit every pathological protein that is the driving force behind the mutation. Basically, we are building an atlas by sequencing thousands of patients, the genome of thousands of patients of every disease, in order to get a roadmap to know how many mutations are driving the disease of each category. So breast cancer, 5,000-10,000 patients will be sequenced, Alzheimer's disease, heart diseases, inflammatory diseases of the bowel, and so on and so forth. That's true only for diseases that are dependent on mutations, but there are diseases that are only partially dependent on mutations. Think about COVID. So, but in COVID too, you can have two patients at the age of 70. One will have the disease as a very easy disease. He will pass through it very easily, and one is going to die. Why is it? It's also probably embedded in the genome, in the genetic repertoire of the patients, in other diseases that the patient has. So I think that the new approach is going to unravel a lot of information about the pathogenesis of the diseases, not all of them, of course, and pave the road for the development of novel and very sophisticated drugs. And the idea of these drugs that they are going to be very specific. They are going to be like bullets directly to the target, because think about it, if we are treating a patient with chemotherapy, it's like shooting with a cannon on a fly on the wall. You know, chemotherapy and radiotherapy are extremely heavy weapons that we are using against cancer, for example, where we can use much sharper tools that will have much lesser and much more moderate side effects. So it's not only that the tools that we are developing will be target oriented, but they will be much less deleterious and harming to the patients. But let's talk about the roadblocks on the way. It's not going to be simple. It's a very long way. We have to sequence tens of thousands of patients. We have to map the mutations, and then we have to develop drugs, and developing a drug is not simple. We have to try the drugs initially in simple systems, then in animals, then in patients, to see whether the drug is efficient, and so on and so forth. But at least with this revolution that started about 20 years ago, only 20 years ago in 2000, with unraveling of the human genome, we have started a long journey to a very interesting and very exciting target. But I want to talk just on the very last issue, and that's bioethical problems of availability of genetic information. The genetic information is the most sensitive information that we have, because it embeds in it many diseases that we still don't have, but may have in the future, psychiatric diseases, and there is a big interest in exposing this information. For example, insurance company would like to know what type of diseases we are going to have in the future in order to insure us. Governments would like to know, universities would like to know, because they want to recruit only the most talented students, and so on and so forth. And on the other hand, we want to keep this information to ourselves. We don't want it to be exposed. Maybe our spouses would like to know what's going on with us before we get married. They want to know how the children are going to look like, and so on and so forth. So you see that genetic privacy is a major issue, because once our DNA is being sequenced, the information in it is truly, truly sensitive and truly, truly explosive. And people think that there will be no way to really protect this privacy, and there will be a big genome leak at the very end. But so this is one issue. On the other issue, there are many advantages, and think about Angelina Jolie, the very famous and beautiful American actress, that discovered that her mother died of breast cancer, and her aunt, the sister of the mother, died of ovarian cancer. And she discovered that both of them carry a mutation in a gene that is called BRCA1. And BRCA1, or breast cancer number 1, is a gene that carries high risk for development of both breast cancer and ovarian cancer. And she decided to make a test by herself, and she discovered that she indeed carries the gene, and she has therefore a high chance to contract one of those diseases. And she decided to go via a very cruel surgery, removing her ovaries and removing her breast, kind of removing a ticking bomb from her body, protecting herself from the risk. And she, by the way, saved herself, but she did not solve the problem of her children. You know, the children may be carrying the same gene, and the children still cannot remove ovaries or breasts. They might be young girls, and so on and so forth. So you see that the issue becomes awfully complicated. At the end, science is there to solve it by correcting genes by a technology called CRISPR-Cas. If you remember, just a year ago, the Nobel Prize in Chemistry went to two women, to Jennifer Doudna and to Emmanuel Charpentier, who discovered the method to correct genes, to correct mutations, to repair mutations. But this, again, technology is still far away from being implemented, and it carries also a lot of moral issues. I want to conclude, because of shortage of time, by telling you that this revolution of personal medicine is going to change the three pillars on which medicine is standing. I'm a physician, so this is very close to my heart. There are three pillars on which medicine is standing. One is disease, the other one is patient, and the third one is treatment. These are the three columns on which medicine stands. Now, the disease. Until now, a disease was on the left side. You see this traditional painting, a condition that prevented us from getting up in the morning and going to our regular daily function. Let it be fever, let it be paralysis, let it be something. A disease now will be something very different. It might be a mutation. So think about this one. Newly developed blood test can detect cancer 4 years before conventional method. So maybe I have already cancer, but I don't know about it because I have a mutation that in 5 years will bring cancer to the surface, but still it's not there. Is it a disease? I feel healthy. I don't have anything. And what shall I do about it? Let's say that my DNA will be sequenced and people will tell me, hey, Aaron, you have a mutation in an oncogene that may erupt in 5 or 10 years to cause cancer. So you see that the definition of disease is going to change from a physical state in which we have to go to the hospital, to the emergency room, to something that is still very elusive and actually non-existing, or at least I don't know about it. So the definition of disease is going to change, and a disease may become a mutation in a gene that may carry risk for heart attack, for prostate cancer, for anything. Now, treatment, the patient is also going to be different because we can now, if we are able to diagnose the disease very early on, we can diagnose the disease already in the sperm or in the egg. By the way, if you thought of what is pregnancy, here you can see pregnancy. You can see a lot of sperm that are going and attack one egg, and at the end, one will penetrate in, and we should get a fertilized egg, and an embryo will start its development. So maybe we can be able to repair the sperm, or to repair the egg, or to repair the fertilized egg, or to repair the embryo after 1 day or 2 days or 4 days and so on and so forth, or the embryo when it has already a shape. So you see, we don't need to wait with the patient until the patient gets cancer. We might be able to cure him or her already at a very early stage, before he even was born, or before even the parent thought about it. We can repair the sperm or the egg. So this is how the patient definition is going to change. And then the treatment. The treatment is going to change from the traditional pills to changing the DNA. We shall be able to take forceps, imaginary forceps, take a piece of DNA out and insert instead of it piece of correct DNA. So think about it. This revolution is probably the biggest revolution that medicine has undergone. It's extremely broad because it covers the entire field of medicine, and it's going to affect us all still in our lifetime, and it's already on. So people are asking me, and with that I'm going to conclude my short talk. People are going to asking me, hey, Aaron, when the revolution will start? Is it going to be January 1st, 2025? No, we are already in. We are moving slowly, step by step, sequencing genomes, developing drugs, trying to correct genes, and we are already into it. And now what we are seeing is a mixture of two medicine, the canonical old type of medicine that I was educated on when I was a medical student in the 60s and 70s, and the modern revolutionized personalized medicine that have started its journey about 20 years ago, and now we are entering it full speed. So thank you very much for your attention, and I'm wishing you a very successful meeting there in Saratov, and I hope to meet you soon, not sitting in front of my computer, seeing you as a remote audience in the hall, but rather shaking hands physically, looking at you, enjoying meals together, and enjoying museums, the beauty of Russian cities, and so on and so forth, like we have become used to during all our lives. So all the very best to you.
Thank you very much for that impressive talk. So do we have questions, please? Please, Yuri.
Okay. Thank you for very interesting talk. I have two short questions connected with so-called scientific biology methods based on DNA reprogramming. First, could you give a prognosis when similar technologies could appear for treatment in clinics? Not for science, but in practical medicine.
Oh, of course. It's already in the clinic. I'll give you an example. If you have, let's say, a mutation in a protein that causes cancer, let's say RAS, and you want to inhibit it, you know the structure of RAS. So this is a chemical approach. And then you know what is the active site. You can design drugs, small molecules that will fit into the mutated RAS and inhibit its activity. So this is one example. Another example can be correcting a mutation that causes a disease, let's say a genetic disease, sickle cell anemia. It's a genetic disease that in hemoglobin, in the protein that carries oxygen and from the lung to the tissues and then carbon dioxide back from the tissues outside, there is a single mutation. With CRISPR, people are able to change the mutation and to correct the hemoglobin. It was already tried. So these are just two examples. Yeah, we are translating it directly to the clinic. It's practical, it's not theoretical.
Thank you. And the second question. My opinion is that similar technologies looks like nuclear technologies. You can use nuclear technologies, for example, for producing electricity, heat, or producing nuclear weapon. And similar technologies, synthetic biology, can be, for example, used for creation artificial viruses which can act on a specific population. What do you think about this dangerous situation, and could we avoid this similar situation and only use?
I don't know whether I'm going to answer your question, but you know, science has always had two sides. It has the bad side and the good side. So think about the world without nuclear energy. Think about cancer patients. Think about radioactive isotope that we are using for research, but think also about an A-bomb and the damage that irradiation causes. So I think that the purpose of science is, of course, to benefit humankind, but there are people and nations that are abusing it. But that's true for every scientific. Think about the technology that we were just talking about, changing genes. People are afraid that people now will clone human beings, and you know, if there will be another Hitler, there will be a cloning of Nazis, for example. So you know, this is kind of a nightmare. But on the other hand, I think that therefore scientists should talk to one another and come to an agreement about the limits of science. Science is not limitless. There are many subjects that we should not do in science. And I think that that's the beauty of science, that, you know, I'm talking now to you in Russia and into Chinese, and science is an international enterprise. And if the country is a free country, scientists should be free to talk to one another from all nations. It's an international language, and agree among themselves what are the limits of science and what we should do in order to benefit humankind, and what are the red lines that we should cross because we are moving from benefits to harm.
Thank you. Thank you.
Yes, thank you very much. Do we have more questions? So I have maybe one question. So you are talking about the DNA modification and so on. And what about RNA?
Well, RNA is the product of DNA. So
yes,
they are members of the same family. So it turns out that COVID-19 is, you know, the messenger RNA is the predominating technology used by Pfizer and Moderna, but the Russians use a different one. AstraZeneca is still using DNA. They use the viral-based. So it's a matter of technology. I don't think that there is a difference. some have advantages, some have disadvantages. Messenger RNA is a very sensitive material. It degrades very quickly. DNA is much more stable. And we still don't know whether the AstraZeneca and the Johnson & Johnson vaccines, or the Sputnik 5 or the Sinovac, the Chinese one, are better or inferior to Moderna. We still have to look into the data, that not all of them have been published. It's the same principle at the end. We are still in the central dogma of biology, where DNA goes to RNA and RNA goes to protein. We are still on the same path.
Yeah, thank you so much. So it was a great talk and discussion. Thank you.
Thank you very much, and good luck to you.
Thank you. Keep in touch. Thank you.
All the best. Bye-bye.
Bye-bye.